should be able to record today. All right, so I'm gonna start recording. So just wanted to let you know all of the tests have been graded. So you could go ahead and check on it. I forgot to release the answer, but I'll do that after today's lecture. So that way you could be able to compare your answer to the answer that I got. And that way you can kind of see what went wrong or what went right. So you do kind of want to go ahead and look over it, and then just know for test correction will be due on Tuesday if you decide to do test correction on your test. But any questions about anything before we go ahead and get started with the chapter? Yeah, you're 100% are gonna have a quiz on Thursday. So yeah, so you should be expecting a quiz on Thursday. All right, so let's go ahead and get started. For test number four might not happen, but I kind of want to see how this week go, and then I'll see if test four could happen. And for the 3 more quizzes, we probably only have 2 more quizzes left. Like at most, we're gonna have 2 quizzes. I don't think we're gonna have 3 more quizzes, so we should only have 2 more quizzes. All right, so what I'm gonna go ahead and do, go ahead and transfer onto my notes. All right, so that's the problem we left off yesterday. So we're gonna continue on with that problem. So let's go ahead and do this problem. So for this problem, it said Kristen Gilbert was a nurse at a veteran administration hospital in Northampton, Massachusetts. She had a reputation of being particularly good in crisis. If a person went into cardiac arrest, she often was the first person to notice something was wrong, signal a code blue, and administer the epinephrine. Often the patient life was saved. Other nurses became suspicious both because of the number of cardiac arrests when Gilbert was on duty and also the number of deaths. Is there convincing evidence that the proportion of shifts with death for shifts when Gilbert was working is greater than the overall hospital proportion of 0.045? What alpha level should we use? So should we use 0.10? Should we use 0.05? Should we use 0.01? Or should we use 0.001? All right, so this is actually a real case. So what we're trying to do, we're trying to figure out, like, did this person really kill or pretty much kill these people in this hospital? So in this case scenario, what we want to go ahead and do, we kind of want to focus when Kristen Gilbert is around. So if you look at the table is telling us whether or not she was present and whether or not there was a death on the shift. So if you look right here, it's telling you if there's a death on the shift. All right, so first thing we want to go ahead and do, we kind of want to go ahead and do a check for the assumption, because for this one, they don't really tell us how many people, well, they don't really tell us if the data set is normally distributed. So what we have to do, we have to go ahead and check the central limit there. So this is one thing that a lot of you had issue with, because instead of checking the central limit there for proportional data set, you were actually checking the central limit there for pretty much the mean. So you kind of want to be careful with that, because a lot of you, instead of saying n times p times 1 minus p greater than or equal to 10, you were mentioning that n has to be greater than 30, which is not true, because since we're dealing with proportional data set, you want to use the central limit theorem for proportional data set, not the one for the mean. So for this one, we're going to check to see if we have a large sample size. Yeah. But we also want to see if we have a big population. So for this one, we're going to say n times p times 1 minus p. That has to be greater than or equal to 10. And then for big population, we have to do 20 times n, and that has to be less than the, it has to be less than the population size. So those are the two formula we want to use because A, we're testing out proportional data set. Anytime we're testing out proportional data set, you want to check out those two if you have a large sample size or if our population is big enough. So before we actually go ahead and check these assumptions, what I want to go ahead and do, I actually want to go ahead and fill out number 4. Because once we fill out number 4, it should help us enter the number into this formula. So for n, what we want to do, we want to focus only when Gilbert was present for a shift. So how many times was Gilbert present? Cool. They put 257. All right. So how many time or how many people die during Gilbert's shift? So when Gilbert was present, how many people died during that shift? Perfect, 40. All right, so if we do p hat, you do 40 divided by 257. Let me do that in my calculator. They do 40 divided by 257. And you get 0.1556. Oops, kind of ran into each other. So you get 0.1556. All right. Last thing, we want P. So P is a proportion of people who die pretty much overall in this hospital. So if you look over here, it tells us the overall hospital proportion of 0.045. So that's overall how many people die in this hospital, pretty much 4.5%. They put 0.045. All right. Everybody good so far on how I pretty much found all of these notation? Okay, so let's go back to check the assumption. So to check the assumption, we're going to do n, which we said was 257, multiplied by p, which is 0.045, multiplied by 1 minus 0.045, and we want to see if that's greater than or equal to 10. So I'm going to do that in my calculator. So do 257 multiplied by 0.045, multiply by 1 minus 0.045. If you look at that, we get 11.04, which 11.04 is greater than 10. So we could say we have a large sample size. Oh, so the way that we get 40 is from here, because essentially it's kind of like a conditional probability. You only want to focus on Gilbert. So that's Gilbert pretty much data set. So we only want to focus when Gilbert is present. So since we want there to be a death on her shift, pretty much we're focusing on the 40 because that's how many times there was a death and she was actually working in the hospital. So pretty much we're just assign that to Gilbert. So that's where the 40 come from. Oh, the P. Well, the P is over here. Because they tell us that the overall amount of people who die in this hospital, So we're going to assume that's the pretty much the population proportion. So we're going to assume the population proportion of death in this hospital is 0.045. So that's the overall amount of how many people die in this hospital. So what we kind of want to see, if Gilbert Kristen, if her proportion of death is the same at the hospital. Because if they're the same, that means pretty much she had nothing to do with it. But if we kind of notice that when she's around and there's more people dying, then we can kind of assume that, hey, the reason why more people are dying when she's around is because of her. She's like the only common factor. All right, so up here we're gonna check to see if we have a big population. So for a big population, we do 20. You multiply that by n, which we said was 257. And let's see what do we get. So 20 times 257, you get 5140. All right, so if you look at this one, the population are pretty much people who go to this hospital. So you kind of have to think about it. Is there more than 5,140 people who go to this hospital? So the answer should be kind of like yes, there should be more than 5,140 people who go to this hospital. So we should have a big enough population. So since the population is big enough, and since we have a large sample size, we're going to say that this is approximately normal. All right, so that's it for 1. Any question in regard to 1? All right, let's go on to 2. It says, in a sentence, describe the parameter that is being tested. So the parameter that's being tested is the proportion of death of this hospital. So that's what's being tested, the proportion of deaths of this hospital. Because we want to see the proportion of deaths of this hospital, is it different from Kristen Gilbert? Because if it's the same, then we kind of know like, okay, she didn't have anything to do with it, because if she's around and if she's away, the proportion is the same. But if the proportion is significantly higher when she's around compared when she's not around, then we kind of know something is up. All right, so up here we're going to do the alternative and null hypothesis. So to do that, we're going to do step number 3. So we say P. So what we want to do, we want to compare to see if Kristen Gilbert proportion is the same as the hospital. So we're going to say that the proportion of death when Kristen Gilbert is around for the null hypothesis, we're going to assume that her proportion of death during her shift is the same as the hospital overall proportion of death. So we're going to say they're the same. But for the alternative, what we want to do, we want to put our claim. Cool. So if you look at our claim, it said the depth of shift, the proportion of shift with a death for a shift when Gilbert was working is greater than the overall hospital proportion. So we don't think that her proportion is equal to the hospital proportion. What we're thinking of that her proportion is significantly higher than the hospital proportion. So what we want to do for the alternative hypothesis, we want to say P is greater than 0.045. All right, so that's my null hypothesis. That's my alternative hypothesis. Any question for my null or alternative hypothesis? All right. Well, for this one, the reason why we don't put not equal to, like the primary reason why we don't put not equal to, it told us specifically is greater than. So they told us that they think that the proportion of deaths when Kristen Gilbert is around is greater than 0.045. Because if you kind of think about it also logically, like it's not a bad thing if her proportion of death during her shift is actually lower than 0.045. That's actually like a good thing. But what the nurses and everybody around her are kind of becoming wary of, they're kind of worried that like when she's around, more people are dying or more people are going into cardiac arrest. So that way we're not putting not equal to, because they told us like explicitly like we want greater than. But also if you kind of think about it logically, like it's not a bad thing if it's less than 0.045. It's a bad thing if it's greater than 0.045. All right. So let's go ahead and do this. So remember, you could do this in the calculator, but you kind of want to just do it to kind of get a feel for it. So mu of p hat is equal to 0.045. If you look at sigma p hat, that's equal to square root of 0.045 multiplied by 1 minus 0.045, all divided by n, which n is 257. All right, so I'm gonna go ahead and just do that in my calculator. I trust that you're able to do that in your calculator too. So 0.045 times 1 minus 0.045. Divide that by n, which is 257. All right, so we get 0.0129. P is the proportion of people who would die. Well, P is the proportion of people who died during her shift. All right, so up next we're gonna do Z. So we're gonna calculate the test statistic. So we're gonna do P hat. So we already calculated the P hat to be 0.1556. And we already calculated mu of P hat to be 0.045. And then sigma of P hat, well, we just calculated to be 0.0129. So like one thing I kind of want you to notice, let me change this to better highlight. So if you look at the number to the left, that's the proportion of death when Kristen Gilbert is around. So hers is around 15%. When Kristen Gilbert is not around, the overall hospital is essentially 4.5%. So if you look at her percentage, so hers is 15%, roughly 15%. And if you look at the hospital proportion of death is 5%. So what we're trying to do, or we're trying to see, is that's a significant difference. So we're trying to see is that pretty much roughly 10% of difference. Is that a significant difference to cause worry for us? So what I'm gonna go ahead and do, I'm gonna let the calculator get the test statistic for me. So I'm gonna go to my TI-84. So we'll go over TI-84. There you go. All right. So for the TI-84, I want to go on. I want to go to stats. We want to go where it says tests. And we're going to do a one prop Z test. So for P naught, it's going to be 0.045. For X we got it to be 40. For N, we got it to be 257. And lastly, we're going to put greater than, because that's our alternate hypothesis. Our alternate hypothesis says greater than. We go over to calculate. All right, so if we calculate this, we get Z. Z is equal to 8 point, and let's round this up to 2 decimal places. So that's 0.56. So if you look at that, you get Z is equal to 8.56. So that's a pretty big Z-score, because it's telling us that's a huge difference. There's a huge difference between P hat and mu of P hat. But up next, we're going to go ahead and do, we're going to get P value. So I'll put right here, P value. So the p-value that we got is 5.90845 e to the negative 18. So as soon as you see that your p-value is bigger than 1, automatically something should be ringing in your head to tell you, okay, this shouldn't be true, that this should be in scientific notation, which it is, because it's saying e to the negative 18. So something in your head, as soon as you see that p is bigger than 1, you should know that this is in scientific notation, not in standard notation. All right, so those are the only two things I want to get, the z-value and p-hat. But any question I got z-value or p-hat from the TI-84? All right, so let me go back to my notes. All right. So if you look at my p-value is 5.908453 e to the negative 18. So that means you have to get the you have to get the decimal place and move it 18 places to the left. So that's 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, so if you move the decimal place 18 places to the left, that's what you get. So if you look at the p-value, that's practically 0%. Because if I tell you to round it off to like say 4 decimal places, it could be 0.0000, which is just 0%. All right, so let's go ahead and fill out number 6. So for this one, is this a left toe test, a right toe test, or a two toe test? Cool, perfect, right. So say the right toe test. So I'll put the p-value right here. So 1, 2, 3, 4, 5, 6. Cool. Yes, we'll be able to put it in. Cool. All right. So we'll say p-value is 0.000, alpha. All right. So if you look at my alpha, for my alpha, they kind of left us to make the decision. So they kind of told us like, hey, it's up to you to choose which alpha level do you want to use. So for this one, kind of remember alpha level is the probability that we make a type 1 error. So type 1 error is when you send an innocent person to jail. So for this one, kind of think about it, if you're a jury, like which of these alpha level would you want to use? Like, do you want to use 0.10, which means you don't want that much evidence? Or do you want to use 0.001, which means that you want a lot of evidence? So which one do you think I should use, 0.10 or 0.001? Yeah, so for this one, you kind of want to use 0.001 because we want a lot of evidence to kind of prove that this person did it. Because if they do prove that this person did this, then most likely she's going to go to jail, which she actually went to jail for. So we're going to say it's 0.001. So which one is bigger, my p-value or my alpha? Yeah, so if you look at 0.001, it's way bigger than 0% practically. So we're going to say p-value is greater than alpha. So in this case scenario, we say reject the null hypothesis. So right now what we're doing, we're rejecting the null hypothesis. So I'm saying this is not true. I'm saying the null hypothesis is not true, and we should conclude the alternate hypothesis that when Kristen Gilbert is around, the proportion of death in the hospital pretty much skyrocketed, because when she's around, it's almost 16%, but when she's not around, it's 5%. So when we reject it, we're saying that that's a significant difference. That 10% of difference is a significant difference to warrant that something is not right. So now we're going to do is just write the conclusion. So we'll say, So here, let me type it out. So say there is strong All right, so that will be our answer for the Kristen Gilbert problem. Any question in regard to that? All right, sweet. Well, for the alpha, if you remember from chapter 10.1, alpha just represent the chance that you can make a type 1 error. So in this case scenario, a type 1 error is you send an innocent person to jail. So in this case scenario, since we're kind of pretending that we're the jury member and we're the one deciding if Kristen Gilbert should go to jail or if we should let her out free, we're saying that we kind of want to minimize the chance of making a type 1 error because we don't want to send an innocent person to jail. So that's why we kind of want it to be 0.001 because the lower it is, the more evidence we need in order to kind of prove that this person did it. But since the probability of her doing it and still being close to the population proportion of death for the hospital, it's very unlikely that we just said we have to convict her because her value is super low compared to the alpha. All right, so let's go ahead and do this last one, and then we'll move on to 10.3. So for this one, a certain drug claimed that less than 20% of their patient will experience side effect. A researcher is skeptical of this claim and run a clinical trial of 400 patients was done. Of the 400 patients, 68 experienced side effects. Can the company claim that fewer than 20% will experience side effects? All right. So for this one, I'm going to do a little bit different. We're going to do step number 2 first, then go step number 4, and then do step number 1. So first thing we want to do for step number 2, in a sentence, we want to describe the parameter that is being tested. So the parameter that's being tested, oops, here it is. The proportion of patient who experience all right. So that's what we're testing. So we're testing the proportion of patients who experience side effects. So that's number 2. So in a sense to describe the parameter that's being tested, the parameter that's being tested is the proportion of patients who experience side effects using this drug. So up next, we're gonna do number 4. We're gonna get the N, the X, the P hat, and then the P. So for this one, how many patients did they have in their clinical trial? Yeah, 400. So we'll put N is equal to 400. Of those 400 of those 400 patients, how many of them experience side effects? 68. So then if I want to find p hat should be 68 divided by 400. So I'm going to go ahead and quickly do this. So 68 divided by 400. So you get 0.17. Lastly, what we want to do, we want to get P. So P is pretty much going to be the proportion of people who get side effect from this drug. So what are they claiming? Yeah, 0.20. Everybody good so far with this? 400 for N, X is 68, P has is 0.17, and P is 0.20. All right. So next thing we're gonna do step number one because we want to check the assumption because I want to see did they do enough in order for us to be able to assume that this data set is approximately normal. Because if you look at the data set, they don't tell us that this data set is normally distributed. So we had to check once I get the central limit there to see if I could say it's approximately normal. So I had to check to see if we have a large sample size. And we had to check the big population. So let's do the large sample size. So for the large sample size, what we want to do, we want to do N times P times 1 minus P. So we get N is 400. P is equal to 0.20. And then you do 1 minus 0.20. So let me go ahead and check to see what do I get when I do that math. So 400 times 0.20 times 0.80. All right, we get 64. So if you look at 64, 64 is definitely greater than 10. So we say we have a large sample size. Up next, what we want to do, we want to check big population. So for big population, we have to do 20 times N, which is 20 times 400. So we kind of want to check to see if our population has a sample, well, if our population size is bigger than 8,000. So for this one, since essentially they're not really kind of limiting who could be a patient, essentially anybody could be a patient. So we're going to assume that there is more than 8,000 patients out there for this drug. So we're going to say we have a big population. All right, so since we checked the central limit there and we said we have a big population and we have a large sample size, for this one, the central limit there we're going to say is approximately normal. All right, so let's go ahead and do the null and alternate hypothesis. So for the null hypothesis, it should be easy because you put P and whatever we say over here, 0.20, and then you go P 0.20. So for this one, what do you think we should put for the alternate hypothesis? Should we put not equal to, greater than, or should we put less than? Well, for this one, who are we trying to prove it for? No, we'll do less than. So you do less than. So what we want to do, we kind of want to prove that this pretty much drug is telling you the truth. So we want to prove that the drug is telling you the truth. So we're going to say P is less than 0.20. So let's go ahead and do this next part. So we say mu P hat is equal to 0.20, We're going to go ahead and find sigma p hat, which is 0.20 times 1 minus 0.20, all divided by n, which is 400. So let's go ahead and find that. So you get square root of 0.20 times 1 minus 0.20 divided by 400. You get 0.02. Everybody get 0.02 as my sigma p hat. So we'll do p hat, which is 0.17 minus 0.20 divided by sigma p hat, which is 0.02. So this one's actually negative 0.03 over 0.02. If you actually do 0.03 divided by 0.02, you actually get negative 1.5. But if you don't believe that, let's do it in our calculator. So I'm going to transfer over to the TI-84. All right, so in TI-84, we go to stats, we go to tests. You want to go over here to the one prop data. If I were you, I will already start taking notes of this because in chapter 10, we're going to be learning a bunch of different function in the calculator. And that's not even included chapter 11. Chapter 11, we're going to learn more function in the calculator. So you do kind of want to start taking notes on when to use these functions, but because once we get to like chapter 12, you're probably going to have already like 10 functions that you have to use in this calculator. So you kind of want to start writing them down so that way you know which one to use. All right, so if you look right here, I put P is equal to 0.20, X is equal to 68, N is equal to 400, and we're going to say less than. So we go ahead and calculate. All right, so if you look at it, we got Z equal to negative 1.5, so I got that one correct. So if you look at the p-value, we got p-value equal to 0.0668. So we got Z equal to negative 1.5. We got p-value equal to 0.0668. All right, so up next, we're gonna go ahead and do, we're gonna go back to my notes. Everybody good so far? I got p-value equal to 0.0668. All right, so now what we're gonna do, we're gonna decide to see if this is a left toe test, right toe test, or a two toe test. So what type of test is this? Cool. So you got left toe test. So we put 0.0668 here. All right, so let's go back up here. All right, so if you look at it, do they give me a alpha level or do they give me a significant level? Okay, well, if you look at it, they don't give me the alpha. So anytime alpha is not given, alpha is supposed to automatically be assumed that's 0.05. So anytime alpha is not given, just assume that it's going to equal to 0.05. So I'm going to assume this is 0.05. So if you look at it, if you compare my p-value to your alpha, which one is bigger, p-value or alpha? Oh, thank you. So yeah, so p-value is definitely bigger, so we failed to reject. So for this one, we'll say there is not enough evidence to say that the proportion What was that? 20%. Cool. All right, so for this one, put there is not enough evidence to say that the proportion of side effect for this drug is less than 20%. Patient. Well, it doesn't mean that the alternative hypothesis was wrong. It means we don't have enough evidence to prove the alternative hypothesis. So based off of this evidence, we didn't have enough. We didn't have enough information to kind of say that the alternative hypothesis is correct. So pretty much we're going to say that the null hypothesis is correct. That is somewhere in 20%. All right. So the way that you could tell if it's a left tail, right tail, or two tail, pretty much all you have to do is look at the alternative hypothesis. If your alternative hypothesis is greater than, is a right tail. If your alternative hypothesis says less than, is a left tail. If your alternative hypothesis says not equal to, then it is a two tail. Like that's how you're able to tell if it's a left tail, right tail, or two tail. If your alternative hypothesis is greater than, is a right tail. If it says less than, is the left tail. If it says not equal to, is a two tail tail. All right. So that's it for that last problem. Any other question in regards to that last problem? Wait. All right. Up next, we're gonna go ahead and we're gonna switch it up, and we're gonna be doing hypothesis testing for the mean. So for hypothesis testing for the mean, if you look over here, pretty much I have them all labeled for you. So if it's a two tail, mu should not equal to whatever the number is that we think. If it's a left tail, it should say mu is less than. If it's a right tail, it should say mu is greater than. So our null hypothesis and alternative hypothesis, the only thing that changes instead of us putting p, we're replacing the p because now we're not testing the proportional data set. Now we're going to be testing the mean of the data set. So remember, we're switching over. So you kind of want to make a mental note, like how do I know what am I testing? Because that's going to be where you read the problem and are able to read the problem and see that it's telling you that you're testing for the mean now. All right, so for the hypothesis test, like the basic step is first you want to do the state the null and alternative hypothesis. Step number 2, get the test statistic. Step number 3, get the p-value and interpret the p-value. Step number 4, you want to state your conclusion, and that's where you just say, do we have enough evidence or do we not have enough evidence? But it should be the same step that we did before. So up next, I'm going to show you the test statistic. So the test statistic, it should be very familiar to you because the test statistic is essentially what we did when we went over chapter 8.1, or sorry, 8.2, one of those two. So for chapter 8.1, if you remember, we were finding what's the probability if we randomly select so many people or so many objects, what's the probability of that occurring? And if you remember, we found the z-value, and then we converted that z-value to a probability. So we're doing exactly the same step, but we're just calling it something different. So for this one, this is our test statistic. In order to get the test statistic, you're gonna get x bar subtracted from mu naught, and then divided by sigma of x bar. And for this one, you just know sigma of x bar is equal to sigma divided by square root of n. So you do have to remember to adjust that. So then let's go over the central limit theorem. So here is the central limit theorem that a bunch of you were putting for proportional data sets. So remember, this central limit theorem, you only apply it if we know the parameter is the mean. or standard deviation. If it's not the mean or the standard deviation, you want to do it for proportional data sets. So you kind of want to make note of when do I use the central limit theorem, where I have to do n times p times 1 minus p, or when do I have to use the central limit theorem when I have to check to see if n is greater than or equal to 30. You use the central limit theorem when n is greater than or equal to 30 when the parameter you're testing is the mean or standard deviation. All right, but I kind of already went over that, so let's move over and let's do a problem. All right, so for this one said the board of a major car company required that the mean wait time a customer for service call is at most 3 minutes. To make sure that the mean wait time is not exceeding the requirement, an assignment manager tracked the wait time of 45 randomly selected calls. The mean wait time was calculated to be 3.5 minutes. Assuming the population standard deviation is 1.5 minutes, is there sufficient evidence to say that the mean wait time is longer than 3 minutes with a 2% significant level? All right, so for this one, what are we testing? Like, are we testing the proportion of wait time? Are we testing the mean time that they wait? What are we testing? But would that be like the mean wait time or, oh, yeah. So if you look at it, we're testing the mean wait time. So that's how we know we're not gonna do what we did in 10.2. Now we're gonna do what we're doing in 10.3. So we are testing the mean wait time of this service call. So yeah, so we're testing the mean wait time of this service call. Perfect. So let's go step 4. So step 4 says find the value for n, x bar, mu, and sigma. So for this one, how big of a sample size did they get? Wait, 45. All right. Let's do an easy one. What do they tell us the standard deviation of the population is? Cool. 1.45. All right. So up next, this is like the kind of the toughest part for students because pretty much we have two means. We have X bar, which is the sample mean, and then we have mu, which is the population mean. So what my suggestion is for you, first find X bar. X bar is always what information did they get from the sample. So if you look at the mean wait time that they collected from the sample, it said the mean wait time was calculated to be 3.4 minutes. So that's my X bar. Because they tell us that they randomly selected 45 phone calls. And then from those 45 selected phone calls, they found the wait time to be 3.4 minutes. So that's the sample mean. If you look at the population mean is what they're trying to claim. So they're trying to claim that their wait time is 3 minutes. All right. Everybody good with 4? All right, so let's go ahead and check down number 1. So we want to check for assumption. So first thing we want to kind of read is anywhere in the problem did they tell us that this distribution is normal? So if you read through the problem, they don't tell us that this is a normal distribution. So since they don't tell us it's a normal distribution, we have to check the central limit theorem. So for the central limit theorem, all we have to do is just check to see if n is greater than or equal to 30. So if you look at my n is 45. So I have to check to see if 45, is that greater than or equal to 30? And the answer for that is yes. So since we could say 45 is greater than or equal to 30, we're going to say our distribution is approximately normal. All right, and that's it for checking for assumption. So for checking for assumption, the only assumption we have to check is if n is big enough, and the answer for that is yes. All right, so let's do step 3. So we're gonna do the null and alternate hypothesis. So you should already know we're testing out mu. So this should be mu is equal to 3. So what do they want us to check? So should we say it's greater than 3, less than 3, or should we say it's not equal to 3? Yeah, because since they say longer, since they're claiming that they think that it's actually longer than 3 minutes, we're gonna put greater than. All right, so let's go ahead and do some basic things. So we're gonna do mu of x bar is equal to mu, which is equal to 3. So this is 3. Sigma of x bar is equal to sigma, which is 1.45 divided by square root of 45. So we're gonna say 1.45 divided by square root of 45. And you approximately get 0.22. So that's my standard error. So the last thing we're gonna go ahead and do, we're gonna find the z-value. So for the z-value, we're gonna say 3.4 minus 3, and you can divide that by sigma divided, well, sigma x bar, which is 0.22. So once again, what we're doing, we're looking at the 3.4 and at the 3, and we want to see, is there a big difference between the two of them? And that's what our z-value is going to tell us. So in order to do this, I'm going to let the calculator do the rest of the work for me, because there's actually a nice function in the calculator that will do the test statistic for you, and will do the p-value for you. All right, so once again, you're going to go to stats. You're going to go to tests. Cool. So for this one, if you look at the very first one, we're going to use the z-test. So this is the second function that we're going to use in chapter 10. So right now we should know one prob z-test. Now we're going to add a z-test. So for the z-test, it's going to ask you, do you have data or do you have the statistic? If you have mu, sigma, x bar, and n, then you have the statistic. So if I have those 4 information, you have the statistic. But if I were to give you a raw data set where I don't give you what the sample mean is or the sample standard deviation, then you want to choose data. So for this one, since we have all the stats, you choose stats, go down, we put mu, which is 3, we put sigma, which is 1.45. So for this one thing you have to be careful, for this one, you always put the original sigma. You don't do sigma divided by square root of n, because if you look in the bottom, where it asks you for n, that's why it's asking for n, because it automatically gonna do that for me. So it's gonna calculate sigma of x bar for me. So there's no need for you to calculate it. The calculator will calculate it for you. Lastly, you go to greater than. Cool. All right, any question on anything I input into this calculator? All right, so for this one, you have to kind of change it up a little bit. I'm gonna go to draw. Here, must have something on this. All right, so let's try that again. So lead test, I'm gonna go to draw. All right, so if you look at it right here, they give me the Z value. So they tell me Z is equal to 1.8505. But also if you look right here where it says P, that's my P value. So I'm gonna put P value is equal to 0.0321. So if you look at it, it gave me Z, which is 1.8505. It gave me P value. But the nice thing about doing draw, if you look at it, which side of the tail did it shade? Did it shade the left tail, right tail, or did it shade both of the tail? It shaded the right tail. So that's why whenever you say greater than, that's why it's always a right tail, because it shades the right side to it. All right, but that's it for the calculator. Any question in regard to the calculator before I move on and go back to my notes? All right, no question. Perfecto. All right, so while you were gone, I just put that Z is equal to 1.8505. I also put that the P value is 0.0321. I also put right here, we have a right tail test, and let me put 0.0321 there. All right. So I'm gonna go back to the problem and I'm gonna see, do they give me an alpha? So for this one, do they give me an alpha or a significant level? Cool. So yes, so they do give me a significant level. Also, if you notice, they say 2%, so that should be 0.02, not 0.2. If you put 0.2, that's essentially telling me the significant level is 20%, which is significantly different from 2%. So you do have to remember that you have to put 0.02 in order for it to be correct. So we'll put 0.02. So which one is bigger, p-value or alpha? P, perfect. So since P is bigger, we say fail to reject HO. So let's go ahead and do that. So when we fail to reject HO, we're saying there's not enough evidence to pretty much say the alternative hypothesis is correct. So it could be saying, hey, there is a change, but it's not a significant change for me to warrant saying that it's significantly higher than 3 minutes. So in this case scenario, we're gonna say there's not enough evidence. So we'll say, here, I'll type it up. So we'll say, there is not enough evidence to conclude well, like the reason why if you manually calculate the z-value or if you calculate with the calculator, the thing is the calculator is always gonna be more accurate and gonna be correct because for the calculator, never round off any value. Because essentially, whenever we're calculating the z value by hand, essentially just rounding off error. But when the calculator does it, the calculator uses every single decimal places, so it doesn't cut it off to like 2 decimal places or 1 decimal places, something like we do. So that way, when you calculate it manually, but if you calculate with the calculator, it will be slightly different. But it shouldn't be significantly different. Like if you're getting 2.15 and the calculator getting like 2.13, that's fine. But if you're getting 2.15 and you're getting like 21.5, then you have to worry about that. All right. So that's it for that last problem. Any question regard to the last problem? Yeah, and if you look at it from the calculator, we get 1.8505, so it's not significantly different. All right, so let's go on to the next problem. All right, so for this next problem, so it says the number of years it took a random sample, the number of years it took a random sample 33 former smoker to quit permanently is listed. We know the population standard deviation is 1.5 years. A health agency claimed that the mean wait time it takes smoker to quit smoking is 6 years. A researcher doesn't believe the claim of the health agency and think it is more than that. At alpha equal to 1%, is there enough evidence to reject the health agency claim? All right then, so let's try doing this problem. So let's do n. Or sorry, let's do number 4 and then we'll jump off, or sorry, let's do number 2. So for number 2, what are we testing? Oh yeah, so if you look at it, we're testing the mean, oops, time it takes someone to quit smoking. All right, so we're testing the mean time it takes someone to quit smoking. Also, just like a warning, for a test question or a quiz question, if I ask you in a sentence, describe the parameter that's being tested, if you put the mean, I can guarantee you're gonna get 0 points. I want a sentence describing what are you finding. So if I tell you in a sentence, describe the parameter that's being tested, always make sure that you write it in a complete sentence because I want a sentence. I want to see if you understand the problem. All right, so that's number 2. So let's do number 4. So what's my sample size? How big of a sample size did we get? Cool, 33, perfect. All right, what is the standard deviation time for quitting smoking? Yeah, so 1.5. What are they claiming? Like, how long are they claiming that it takes for someone to quit smoking? Are they claiming it's 10 years? Are they claiming it's 20 years? Are they claiming it's 5 years? How long do they claim that it takes someone to quit smoking with their program? Yeah, 6 years. Perfect. All right. Also, if you notice for this one, do they give me an X bar? All right, so the answer for that should be no, they did not give me an X bar. So they didn't give me an X bar, but if you look at this is data. So from this data, I'm going to be able to get the X bar from this data. So we'll worry about that a little bit later, but just kind of want to introduce you that you're not always going to be given all the information up front. There is going to be some time where you have to pretty much search for that with the information that I give you. So this is one of those cases where you do have to search for it with this data set. All right, so let's go ahead and check for assumption. So do they tell me the mean time it takes someone to quit smoking? Do they tell me that this has a normal distribution? Yeah, perfect, yeah. So when we go to the calculator, instead of using statistic, we're gonna use data. Good job. All right, so in this problem, do they tell me that we have a normal distribution? All right, but that's not the question I was asking. But yeah, so if you look at the problem, they don't tell me this is a normal distribution. So what I had to do, I had to apply the central limit theorem. So for the central limit theorem, like Javier already put down there, n has to be greater than or equal to 30. So since we have 33, which is clearly bigger than or equal to 30, we could say this is approximately normal. All right, so that's it for number one. So we can say our data set is approximately normal because our sample size is big enough. It's bigger than or equal to 30. So let's go ahead and do step number 3. So for step number 3, we're going to do the null and alternate hypothesis. So the null hypothesis, if you label everything correctly, for this one, since we're testing the mean, this is your null hypothesis. You're going to put mu is equal to 6, where it's a mu and 6 right here. Cool. So what are we trying to prove? Are we trying to prove that it's less than 6 years, that it's more than 6 years, or are we trying to prove that it's different from 6 years? What are we trying to prove here? Cool. We're trying to prove that it's more than 6 years. So here it says agencies think it's more than 6 years. Cool. So you put greater than. So if you look at it, since I put greater than, that's telling me we're gonna have to do pretty much a right toe test. All right, so let's go ahead and do this part right here. So we're gonna do mu of x bar. Let's see, where's the mu? All right, so mu of x bar is equal to mu, and mu is equal to 6. I'm going to calculate what sigma of x bar is. Sigma of x bar is equal to sigma, which is 1.5 divided by square root of n. Square root of n is 33. So let's do 1.5 divided by square root of 33. That's not 33. That's 3. All right, so you get 0.26. Yeah, we'll just say that 0.26. So that's my standard error. So now if I want to find the z value, well, we're going to do x bar minus 6 divided by 0.26. But if you kind of notice, we're missing the x bar. Since we're missing the x bar, now is a good time to do this in our TI-84. All right, but any question before I move on to the TI-84? All right, let's all move on to the TI-84. So for the TI-84, we're gonna go to stats. But instead of going to tests right now, we're gonna go to edit because I have to enter in some data sets. So I'm gonna clean this up. So that should be kind of like a good habit to have. Clean up your list. So that way you don't have no junk in there. So you go 10.7, 3.2, 12.1, 8.6, 9, 8.7, 9.2. All right, sweet. All right, so I enter all the data set into L1. So now we're gonna go over here where it says stats. We're gonna go to test, and we're gonna do a z-test. Remember, the reason why we're doing a z-test, because we have the population standard deviation. If we don't have the population standard deviation, well, I'll show you what do we do in a little bit. So right now what I wanna go over where it says data. So I'm telling you data because I just enter all of my data set into L1. So instead of me having to find the mean by hand, I'm gonna tell the calculator, hey, you find the mean by hand. So if you look at my mu is still gonna be 6. My sigma is still gonna be 1.5. If you look at it, I put L1 because that's where I put my data set in. I put in L1. And if you look at the frequency should be 1 because I only have one list. And if you look at it, we want to put greater than because that's my alternate hypothesis. And here, let's go to draw. But any questions so far for the input on the z-test in your TI-84? All right, so let's go ahead and draw. Cool. All right, so if you look right here on the right hand side, you see the right tail. So if you look at the z value gave me 1.9265. And if you look at the p-value, it gave me the p-value is 0.027. All right, so let's see. So after you put in the data set, you go to stats, you go to test, you go to z-test, and you tell it data, you put in the mean, you put the sigma, you put L1 for the list, and then frequency is 1. And also I'm gonna do calculate this time. And like the good thing, if you do calculate, it'll calculate all of this other good stuff for you. Like it'll calculate the mean. So now we know the sample mean is 6.5. But yeah, like it calculates like the z value, which is 1.9265. It also calculates the p-value, which is 0.027, and it calculates the sample mean. So if you wanted to know what the sample mean was, well, you got it. All right, but that's it for the calculator. Any questions so far on the output of my calculator? Well, the reason why we chose mu, because that's what they're claiming, because they're claiming that they're because if you look at what they're claiming, if you look at the second sentence, or sorry, the third sentence, It says the health agency claimed that the mean time it takes smoker to quit smoking permanently is 6 years. So that's what they're claiming. They're claiming that if they take their program, it's gonna take them 6 years to quit permanently from smoking. So that's why you say mu is 6. Right, cool. And if you got a syntax error, like I can't help you with that right now. If you can, just drop by my office hour, and I'm sure I could kind of figure that out. But unfortunately, right now, can't really help syntax errors. All right, so if you look right here, I put z equal to 1.9265. I also put my sample mean is 6.5. So if you look at the sample mean, if you look at the population mean, there's not that much of a difference because pretty much 6.5 and 6. So we have p-value 0.027. So now we're gonna look for alpha. So let's look for alpha. All right. So what was the alpha that was given for us here? All right, cool. We already got it, 0.01. All right, so we got p-value. P-value is 0.027. Alpha is equal to 0.01. So which of the two is bigger, my p-value or my alpha? Yeah, p. So I also kind of forgot, this is the right tail test, the 0.027. All right, so p-value bigger than alpha. Since p-value bigger than alpha, that means we fail to reject. So even though there is a difference, it's not a significant difference because we do know, like, we're sampling from a sample. So we know it's not 100% accurate. So even though we do see a slight difference between 6.5 and 6, there's not a significant difference for us to kind of warrant saying that there is a significant difference that is significantly greater than 6 years. So for our interpretation, we're going to kind of put that. So say there is not enough evidence to support the claim that all right, so that's it for that question. Any question for that last problem? What do you mean by you got a different standard deviation? Okay. Yeah, well, if you wouldn't have gotten the same standard deviation that I got, most likely it would have been that you enter in the data set incorrectly. All right, so for this one, if you look at my conclusion, you say there is not enough evidence to support the claim that the mean year that it takes someone to quit smoking permanently is greater than 6 years if they use this program. So kind of notice the conclusion. The conclusion are not just like one word, two word, three word. You kind of want to practice on these, making full sentence for that way it makes sense. So in a test or in a quiz, like this is what I will expect you to write. It's not gonna be identical to what I have, but it should be pretty much hitting the same focus part. Like it should say there's not enough evidence, there is enough evidence, and then you want to mention something about the alternate hypothesis. All right. So what I want you to do, I oops, didn't want to move that up. All right. So what I want you to do, I want you to try this next problem. So I'll give you a head start and then we'll do it all together. But do practice on this problem. Because the thing is, if you don't practice, you're not going to get good on this. And if you're planning on practicing during the test, well, I'm going to be seeing you next semester for stats class because that's not going to work. So do practice for that way you could get some practice in. So that way you make sure that you do understand how does the formula work, how do we enter everything for that way you're getting practice. So practice on this one and then we'll go over it together. All right, so let's try doing this problem. So before we do check for assumption, I kind of want to just go and label everything. So let's first go and label everything. So n is, oops, 33. X bar in this case is 30, or 133. And if you look at this one, you get mu in this case is 135. And sigma is 33. Oh, yeah, thank you. Yeah, that should be 32. Yeah, thanks, Stephanie. All right, so that's what you should have gotten. And like for this one, you have to carefully read it. Because if you look at the second sentence, it says to test a claim, you randomly select a sample of 32 systems and find the mean activation temperature to be 133. So they took a sample of 32 and then they got the 133 from that sample. So that's how you know 133 is from that sample. Yeah, we got a dot. All right, everybody good with that? All right, so if you look at step number 2, in a sentence describe the parameter that being tested. The mean activating temperature for the sprinkler system. So that's our that's the parameter we're testing, the mean activating temperature for the sprinkler system. So that's what you want to put for step number 2. And if you look at step number 2, since we're testing the mean, that means we want to use the central limit theorem of n is greater than or equal to 30. So because we're testing the mean, that's why we use the condition that n has to be greater than or equal to 30. If we would have been testing the proportional data set or some proportional data set, that's where you want to do n times p times 1 minus p. And that's where you have to check to see if you have a big population. But in this case, since we're testing the population mean, that's why you want to do n is greater than or equal to 30. Because the reason why you want to check to see if n is greater than or equal to 30, because if you read the problem does not tell you that the data set is normally distributed. So in order to check to see if it's normally distributed, we have to see if, sorry about that, it went local. Oh, wait a minute. We have to check to see if n is greater than or equal to 30. So we have 32, which is clearly greater than or equal to 30. So since that checks out, we can now say it's approximately normal. Yeah, that'll be fine, Stephanie. All right, so let's do the null hypothesis. They say mu is equal to 135. All right, so for my alternate hypothesis, what should I put for my alternate hypothesis? All right, so for this one, what you want to do, you want to put that it's greater than 135. Because if you look at it, essentially they're skeptical about this. So they're kind of skeptical of this one. So you don't want to put not equal to, because they kind of give you a kind of clear cut direction on which way it should go. But essentially what you want to do is you kind of figure out which way to do it for. So what you want to do, you just want to put greater than. So for this one, the null hypothesis means that it's not working. So the null hypothesis means that this is not working. If the alternative hypothesis is true, that means that this sprinkler system is working. So for this one, we're going to say mu is greater than 135. All right, so let's go ahead and just calculate some of these things for part 5. So for part 5, we say mu of x bar is equal to 135. Sigma of x bar is equal to 3.3 divided by 32 square root. So let's do 3.3 divided by square root of 32, which is that equal to 0.58, yes, 0.58. Everybody go mu of x bar and sigma of x bar. All right, so what we're gonna go ahead and do, we're gonna go 133 minus 135, and we're gonna divide this by 0.58. But for us to get a more accurate number, I'm gonna let my calculator find the test statistic and also give me the p-value. So let's go to the calculator. So we go to stats, we go to test. Remember, since we're testing out the mean, you want to do the z-test. So remember, we don't have data anymore, we have stats. So change it to stats. So we say mu is 135. We say sigma is 3.3. We say x bar is 133. We say sample mean is 32. And for this one, we said greater than, and we go to calculate. So if you look at it, we get negative 3.43. For this one, is this a left toe test, right toe test, or a two toe test? Perfect, right toe test. So if you look at it, it gave me a p-value of 0.9999 or 0.9997. 0.9997. All right, so that's my p-value. Everybody go with that p-value. All right. So if you look right here, I selected that's the right toe test, and I selected that is a p-value of 0.9997. So 0.9997. If you look at it, we have to figure out what's my alpha. So for this one, what's my alpha? Yeah, 0.10. So if I have a p-value which is pretty much close to 1, if I have an alpha which is close to 0.10 or which is 0.10, which is bigger, p-value or alpha? Okay. All right, so we got p-value. So p-value is greater than alpha. So hopefully for this one, you said failed to reject the null hypothesis. All right, any questions so far in regard to this? All right, so up next we're gonna do the interpretation. So remember for this one, we failed to reject. So we failed to reject the null hypothesis. So that means that these sprinklers are actually not working. Because if they're working, because the thing is, you kind of have to think about it. You don't want sprinkler to kind of go off just for no reason. Because if they go off in less than 135 degrees Fahrenheit, essentially it could go off and we don't actually have a fire. So pretty much when we fail to reject this case, we're saying that the sprinklers are not working. Because if they were working, they will activate after 135 degrees Fahrenheit. But since they're activating when it's below 135 degrees Fahrenheit, it means it's not working. So for our interpretation, you kind of want to say something like that. So we'll say, there is not enough evidence to say that. So the reason why we say mu is greater than 135, because they said the word at least. Because it said at least, so at least means it should be greater than 135. So for this one, we'll say there's not enough evidence to say that the mean temperature that the sprinkler system activate is greater than 135 degrees Fahrenheit. So that's kind of telling me that these sprinkler systems are not working. So like I said, you don't want sprinkler system to essentially be going off at any point. You kind of want them to go off when there's like a real fire. All right, but that's it for that problem that I asked you to do. Any question for this last one? All right, so let's get into the second part. All right, so this is a typo. There shouldn't be an N right there next to sigma. Typo gone. All right, so for this one is hypothesis testing for population mean when sigma is unknown. So we just went over how to do a hypothesis test when sigma is known. So now we're gonna do a hypothesis test when sigma is unknown. So for this one, I'm not gonna go over the hypothesis or the different type of hypothesis because we just went over that. But pretty much what I want you to kind of notice for this one, you want to use the t distribution now, because instead of knowing the population standard deviation, now we don't know the population standard deviation. So if you kind of remember in back when we did chapter 9 point something, when we did confidence interval for the mean, and essentially you could do confidence interval of the mean when sigma is known and sigma is not known. When sigma is not known, you always use a t distribution. So for this one, you do kind of want to pay attention to the sample size, or sorry, the sample of standard deviation, because if we don't know the population mean, you're essentially looking for the sample standard deviation. All right. Cool. All right, so the central limit theorem, still the same thing, n has to be greater than or equal to 30. So let's do this one problem. So for this problem, it says Susan is in charge of quality control at a small fruit juice bottling plant. Each bottle produced is supposed to contain exactly 12 fluid ounces of juice. Susan decided to test this by randomly sampling 30 filled bottles and carefully measuring the amount of juice inside each. She will recalibrate the machinery if the average amount of juice per bottle differ from 12 fluid ounces at a 1% significant level. The sample of 30 bottles has an average of 11.92 fluid ounces per bottle and the standard deviation of 0.26 fluid ounces. Should Susan recalibrate the machinery? All right, so for this one, let's do step 2. In a sentence, describe the parameter that is being tested. So what is being tested? Well, how do they determine they should recalibrate the machinery? Cool. Yeah, so pretty much what's being tested is the average, mean, let's see, average, juice. All right, so what's being tested is the average juice that each bottle get. So essentially we want to measure how much juice did each bottle get, because essentially if they get more than 12 fluid ounces or less than 12 fluid ounces, that's bad news, because essentially if they get more than 12 fluid ounces, that means it get an over pour, and that means they're losing money. If they under pour, that's also bad news, because essentially they're gonna start losing clients, because pretty much they're gonna start seeing that they're not getting 12 fluid ounces, they're actually getting like ripped off. All right, so let's go ahead and let's find all of these good things. So let's find N. What's our sample size for this data set? Cool, 30, perfect. All right, what's our X bar for this? Yeah, 11.92. What's our mu for this? Cool. So yeah, so far we have N is equal to 30, we have X bar is equal to 11.92, we have mu is equal to 12. So now what we have to do, we have to find S, but just remember in tests or in quizzes, like I'm not gonna tell you, hey, you have to use a t distribution, so you're gonna get a sample standard deviation. Like from the problem, you should be able to read the problem and be able to see like this is why is a sample standard deviation. So for this one, our sample standard deviation is 0.26. And the reason why it's 0.26, if you look at it, it comes from this sentence. So if you read that sentence, it said the sample 30 bottle has an average of 11.92. So the 11.92 is referring to the 30 bottle. So since the 30 bottle is my sample, anything that comes from that sample is my sample mean. And then if you keep on reading it, it says, and a standard deviation of 0.26. So once again, the 0.26 is referring to the 30 bottle, which once again is our sample. So since the 0.26 is coming from our sample, we say this is sample standard deviation. So because we have sample standard deviation, that's why we're going to use the t distribution. So you kind of want to make note of that, because some of you on the test messed that up on distinguishing between a t distribution and a z distribution. So you do want to make sure that you know the difference between a t distribution and a z distribution. All right. So also, if you look at the problem, nowhere through the problem, it tell you we have a normal distribution. So once again, we have to apply the central limit theorem. So we have to check to see if n is greater than or equal to 30. So if you look at our sample size, is equal to 30. So you go, is 30 equal to 30? Well, yes, it is. So you say approximately normal. All right, so we're done with 1, we're done with 2, and we're done with 3. So let's go, or sorry, with 4. Let's go to 3. So for 3, if you fill this out correctly, this is your null hypothesis. Mu is equal to 12, mu, and 12. So then what we have to do is to decide which symbol should I put in between mu and 12. So should I say not equal to, less than, or should I say greater than? But you do want to say not equal to because of this. It says differ, so different. So we want to say that it's different from 12 fluid ounces. So we don't care if it's above 12 fluid ounces or below 12 fluid ounces, because in any case scenario, if it's overpouring or underpouring, that's a bad case scenario for us. So we want to say not equal to. All right. Also, if you remember for the T distribution, you need something called degrees of freedom. So degrees of freedom is n minus 1. So if I do n, which is 30, minus 1, you get 29. Everybody good? I got 30 minus 1 is 29. All right, so let's compute this. So mu of x bar, which is equal to mu, is 12. Sigma of x bar, which is equal to s divided by square root of n, is equal to 0.26 divided by square root of 30. So is it 0.26 divided by square root of 30. This is 0.0, and we'll get 3 decimal places for this. So we get 0.047. So now for our test statistic gonna be x bar, which is 11.92 minus 12, and you divide this by sigma of x bar, which is 0.047. All right, so remember, what we're trying to do here, we're trying to see if this is a significant difference. So we're trying to see if from 11.92 to 12, is that a significant difference for us to consider recalibrating the machine? Because if this is something that's pretty close to 12, then we can just say, okay, we don't need to recalibrate the machine, it's close enough. But if this process says, no, it is a significant difference, that we do warrant to pretty much have to do, recalibrate the machinery, then we have to go ahead and do it. So I'm gonna go ahead and do this part in the calculator. That way we could get an accurate answer. Oh, I have to share my calculator. All right, so we go to stats, we go to tests, and we do a t-test. So remember, since we have sample standard deviation, you have to use the t-test. If you have population standard deviation, you use z-test. So let's do the t-test. So for the t-test, if you look at it as for mu, mu is equal to 12. If you look at it as for x bar, so that's 11.92. Then it asks for sample standard deviation. That's what S of x is. So sample standard deviation is 0.26. And n is 30. And if you look at this one, you want to put not equal to. And just for fun, we're going to draw this out. But any question for any of the inputs here? All right. So let's go and press calculate. All right, so if you look at the t-value, we get a t-value which is equal to negative 1.685. So the third t-value, if you look at the p-value that we get is 0.1027. If you look at how many tail does my drawing have, how many tails does it have? Oh, 2. So this is a 2-tail test. So when it asks you to check out for what type of tail does it have, we're gonna say this is a 2-tail test, and we're gonna enter that probability there in 2-tail test. All right, but any question in regard to how to enter this into the calculator? All right, so up next, we're gonna go ahead and go back to my notes. All right. So while you were gone, I enter t is equal to negative 1.685. I also put that this is a 2-tail test, and I got the p-value No. Oops. That's not the p-value. It's 0.1027. So I put the two-tailed test and I put the p-value. Also put the p-value over here. Yeah, you're still in 10.3. All right, so for this one, what's my alpha? Yeah, so if you go back here, they say 1% significant level. So that's 0.01. So if you look at my p-value is 0.1027, my alpha is 0.01. So which one's bigger, p-value or alpha? Oh, finally. So yeah, so p-value is greater than alpha. So p-value is greater than alpha. So we fail to reject. So when we fail to reject, we're saying there's not enough evidence in order to warrant to recalibrate this machine. So we're gonna do our interpretation. We're gonna say there is not enough evidence to say that so for our conclusion, we'll say there is not enough evidence to say that the mean amount of juice in the bottle differ from 12 fluid ounces. So they shouldn't recalibrate the machinery, because the only time they recalibrate the machinery is when we could say there is a significant difference from 12 fluid ounces. All right, and that's it for that interpretation. Any question in regard to that interpretation?
I do have a question.
Yeah, what's up?
So, because I know I'm gonna make this mistake eventually, of using the calculator to find the p. Well, in this case, will be the p-value. How do you not confuse yourself by reading just the question? You know, what gives it away? Does that make sense? I don't know.
Like, let's give it away. That's a T distribution versus a Z.
Yes, there you go. Uh-huh.
Well, pretty much you just go back to just like the basics. So Z distribution, you have to tell you the population standard deviation.
They have to give it. Yeah.
Yeah.
Oh, okay.
And then for the Z distribution, or sorry, for the T distribution, you have to give you a sample standard deviation.
All right, perfect. Thank you.
So you take time of just like reading different type of problem and just kind of distinguishing, hey, like in this problem, they told me the population standard deviation, or in this problem, they gave me the sample standard deviation. So you take a lot of reading and just being able to just read the problem carefully and you're saying like, hey, since they told me this is a sample and this standard deviation came from the sample, that's how I know this is a sample standard deviation versus if you tell us, hey, the population standard deviation is equal to 2 point whatever, then that's your population standard deviation. So you should kind of make like a little mental note, or you put this on your sheet of paper for note. You're saying, hey, you use the Z distribution when the population standard deviation is given. So if you have sigma, but if you have S, you use the T distribution.
Perfect. Thank you.
Yeah, no problem. All right, that's pretty much all the time I have because I only have like 3 more minutes left. So just remember, we're still going on. So far, we already know 3 functions for chapter number 10, and we're still going on chapter number 10. So like I said, like you do want to start making notes about all the function for the different type of problem that we're using. For that way, like, because I'm telling you, once we get to chapter 11, there gonna be more function. Once we get to chapter 12, there gonna be more function in the calculator. So you kind of want to start making sure that you kind of know when do I use like the z test, when do I use the t test, when do I use the one prop z test. For that way, once we go to chapter 12, chapter 11, you're not getting them confused with those functions. So like I'm saying, like there are going to be a bunch of functions coming out. So start taking notes. All right. Any question before I close out this meeting? Test tree is probably not open. I'll just go right now, open it. So it should be open in less than 10 minutes. Any other questions? All right, guys. So I'll see everybody tomorrow. So